Suppose you're given the following acceleration versus time graph. And this acceleration versus time graph might represent the shifting between, say, first and second gear in a car. And you're asked to find the total change in velocity, given that the car starts from rest. So the first thing that we're going to do is we're going to calculate the change in velocity over this first interval of time, this first 5 seconds of time. We'll call this delta V1. And then we're going to calculate the change in velocity between these 2 points, and we'll call this delta V2. Now, to calculate the change in velocity, we're going to use the straight definition of acceleration, or in this case, constant acceleration. Now, acceleration was defined to be the change in velocity per change in time, and this is valid in this case because the acceleration is constant. It's a nice horizontal line. Now, in reality, if this was a car shifting between 2 gears, there wouldn't be this sharp transition. There'd be more of a linear transition between these 2 points. But in this case, we're going to consider an idealized case in which you shift it with this nice sharp transition between these 2 rates of acceleration. Now, the first thing I'm going to do to isolate my change in velocity, which is what I'm looking for, is I'm going to multiply both sides by delta t. By multiplying both sides by delta t, what you can do is you isolate your change in velocity. In this case, we can rewrite this now as the change in velocity equals the acceleration over which the object was accelerating. Now, in this first case, the acceleration was 2 meters per second, and you can go right up to the graph and you can pick that number out. So in this case, 2 meters per second squared. That's the rate at which this object is speeding up, and it speeds up over a time period of 5 seconds. Now notice that this unit of seconds cancels out with this unit of seconds, and when you multiply these two numbers out, you're going to get 2 meters per second times 5, or 10 meters per second. So our change in velocity over that first 5 seconds is going to be 10 meters per second. Now if we go back up to our acceleration versus time graph, this delta V1, or this change in velocity, is going to be equal to 10 meters per second. Now, one of the things that we said is that this object starts out from rest. So the velocity at this point, which we'd call the initial velocity, would be 0 meters per second. And let's just show how we'd go about finding the final velocity at time t equals 5 seconds. And to do that, you go straight back to the definition of what a change in velocity is. Now, we've calculated that our change in velocity over, say, the first interval of time is going to be 10 meters per second. Now, a change in velocity is really just the final velocity minus the initial velocity, so it'd be this delta v is just going to be v final minus v initial. That's the definition of a change in velocity, and it's going to be equal to 10 meters per second. So notice that this, again, just comes down or can be broken down into these two terms. And now when you do this, our initial velocity is 0, which is stated in the problem, so our final velocity over that first 5-second interval of time is just going to be 10 meters per second. So if you go back up to the velocity versus time graph, this velocity at this point would be 10 meters per second. And now our next goal is to calculate the second change in velocity, the change in velocity during which this object is now accelerating at a rate of 4 meters per second. And to do that, we would start off with the same basic equation, that our change in velocity is going to be equal to, we'll call this delta v2, the acceleration over that second interval of time. Now in this case, the acceleration over that second interval of time is going to be 4 meters per second, or 4 meters per second squared, and it's also over a 5-second interval of time. Now notice again that this unit of second squared cancels out with this unit of second, and your change in velocity over that second interval of time will be 4 meters per second times 5, or 20 meters per second. So our second change in velocity now will be 20 meters per second, and we can label that here. Now we're looking for the final velocity at this point. Maybe you call that v final 2, or let's just keep it with a v final. Now we know at this point right here, the velocity initially is going to be 10 meters per second. Now to find the final velocity after 10 seconds, we're going to go back to our definition of change in velocity. So change in velocity, let's say call it 2, we said was 20 meters per second. So over that last 5-second interval of time, the velocity is going to change by 20 meters per second. But remember, the definition of this delta v is going to be v final minus v initial equals 20 meters per second. Now in this case, our initial velocity isn't 0 anymore. Now in this case, our initial velocity is going to be 10 meters per second. So it's going to be whatever our final velocity is minus 10 meters per second equals 20 meters per second. And now what you need to do is algebraically solve this equation by taking this 10 meters per second and moving it over to the other side. To do that, you have to add 10 meters per second to both sides of this equation. And when you do that, what you should see is that your final velocity equals 30 meters per second. 20 meters per second plus 10 meters per second would be your 30 meters per second. And so the final velocity at the end of accelerating is going to be 30 meters per second. Now our next goal is to determine the total distance over which this object travels while it's accelerating at two different rates. And to do that, what we need to do is look at our kinematic equation. Now in this case, our delta x, let's say 1, is going to equal our initial velocity times time plus 1/2 the acceleration times time squared. Now this object starts out from rest, so this v initial times times term is going to equal 0, and so our change in distance, or delta x1, is going to be 1/2 acceleration times time squared. Now in this first case, the acceleration over the first 5-second interval of time is going to be 2 meters per second times a change in time of 5 seconds squared. And what you should see now is that you get 1/2 of 2 meters per second works out to be 1, times 5 seconds squared works out to be 25 meters. And that's going to be the change in distance over the first 5-second interval of time. Now to find delta x2, we use the same equation. Delta x2 in this case equals v initial times time plus 1/2 acceleration times time squared. Now our initial velocity in this case is not 0. In this case, we calculated our initial velocity to be 10 meters per second after that first 5-second interval of time. So we're going to write this as 10 meters per second times a change in time of 5 seconds plus 1/2 of 4 meters per second squared times a change in time of 5 seconds squared. Now when you do this out, notice a few things. Notice that these units of seconds cancels out, so you get units of distance, and in this case it'll be 10 times 5, or 50 meters. Add this to 1/2 of 4 meters per second squared times a time change of 5 seconds. Quantity squared will give you 25 seconds squared. Notice that these units of seconds squared cancels out. When you do this, it's going to be 50 meters, plus 1/2 of 4 is 2 times 25 is 50 meters, or a total change in distance of 100 meters while the car is accelerating at a rate of 4 meters per second. Now the total distance this car travels during that interval of time is going to be 25 meters, during which the car was accelerating at a rate of 2 meters per second for 5 seconds, plus 100 meters, during which the car was accelerating at a rate of 4 meters per second with some initial velocity. So the total distance that this car travels now in 10 seconds is 125 meters. And that's your final answer.